Welcome to the video lecture on area of a triangle. Hopefully you're familiar already with the area of a triangle formula that you learn in geometry that says the area of a triangle equals 1/2 the base times the height. So we're going to start off with a proof of that. So what I have right here is this blue triangle, just any generic triangle at all, and I'm calling the base down here at the bottom B, and I'm dropping a perpendicular down and calling that the height H. Now what I'm going to do to prove this is construct a rectangle around that triangle. And you can see from the symmetry here that I have this triangle right here, triangle 2, has to have the same area as triangle 1 because they form halves, equal halves of this smaller red rectangle. And then if you look over here, rectangle on this side is split in half by the two equal triangles 3 and 4. So what that means is that all 4 rectangles here make up the area of the entire rectangle, this great big one. And what would that area of that entire rectangle be? So triangle 1 plus triangle 2 plus triangle 3 plus triangle 4 makes up the area of the entire shape here. And since it's a rectangle, we know that area of a rectangle is length, which we're calling B, times width, which is what we're calling this height H. So the area of this great big rectangle is base times height, length times width. Now if you notice from that symmetry, since triangle 1 and 2 are equal areas, and triangle 3 and 4 are equal areas, then triangle 2 plus triangle 3 should make up exactly half of the area of the entire rectangle. So triangle 2 plus triangle 3 must be 1/2 of the entire area, base times height. And triangle 2 plus triangle 3 make up the area of the original triangle that we were trying to find the area for. So this proves that the area of that blue triangle must be half the entire base times height. Now that's a formula that's useful if you know the base and the height. So what happens if you don't know the base and the height of your triangle, but instead you know 2 sides and the included angle? So for example, in this triangle right here, I might know this side A and this side B and the angle in between, and we call that SAS, side, angle, side. So how would we figure out the area of this particular triangle? Well, the only place to start would be by this formula that we just talked about, 1/2 base times height. What is the base in this particular triangle? Well, if I think about the base as this bottom side down here, then this base B is actually what I'm calling A. What would be the height of this triangle? Well, the height would be this perpendicular distance right here, and I don't know what that is. So we're going to use a little bit of trigonometry to help us figure out what this height H is. So look at this smaller triangle right here. It's a right triangle because we have that perpendicular being dropped down, and in this triangle we know this side is what we're calling our H, and we also know this hypotenuse that we're calling B. So if we have an angle theta over here in the corner, then we know an opposite side and we know a hypotenuse side. So which trig function sort of relates the opposite and the hypotenuse? Well, that's sine. So if we use a sine function and take the sine of this angle theta, then that has to be the opposite side, which we're calling H, over the hypotenuse side, which we're calling B. Now let's solve this for H so that we know what to substitute in for this H in our formula. So in order to solve this for H, I'm just going to multiply both sides by B, and this gives me B sine theta must equal my H. So now I can substitute in for this H the expression B sine theta. Now when I multiply all of this together, I can't really simplify anything, but what it gives me is a new formula for the area of a triangle, but it gives it to me in terms of the A, the B, and this angle theta. So according to this formula, if you know SAS, 2 sides and the included angle, then the area is just 1/2 the A times the B times sine of the angle theta. And theta can either be acute or obtuse, and the formula will still work. So let's try an example of this. Here's my triangle. I have this side over here, which is 10, this side over here, which is 3, and the angle in between, which is that 120 degrees. So we're given an SAS, the two sides and the included angle in between. We're not told any kind of height at all, so we wouldn't be able to use the 1/2 base times height formula. But I could use this 1/2 AB sine theta formula that we just talked about. So in this problem, my two sides that I know are the 10 and the 3. So I'm going to let my A be the 10, I'm going to let the B be the 3, and the angle in between, this theta, is that 120 degrees. Now you could use a calculator for this, but hopefully by now you know what sine of 120 degrees is by heart. You want to know that from your unit circle. 120 degrees is 90 degrees plus 30 more. So this whole distance here is 120. If you're thinking radians, it's the same as 2 pi over 3. And in terms of our terminal point and our ordered pairs, for any pi over 3 angle, the x value is the 1/2 and the y value is root 3 over 2. And since we're in quadrant 2, the x value would be negative 1/2. So sine of 2 pi over 3, or sine of 120 degrees, therefore is the y coordinate, which would be this square root of 3 over 2. So I'm going to substitute in root 3 over 2 for this sine of 120. And then we just need to simplify. So we have 2 goes into 10 5 times. 5 times 3 is 15. We also have that root 3, and we're left with a 2 on the bottom. So the area of this triangle is 15 square root of 3 all over 2. Now the next formula is also for the area of a triangle, but this time it's for finding the area of a triangle if the only thing that you know are all 3 sides of the triangle, and we would call this SSS. So this would be if you were given a triangle and all you knew were the A, the B, and the C, and you weren't given any heights and you weren't given any angles. So this is Shermans Formula. It says that the area of the triangle is the square root of S times S minus the A times S minus the B times the S minus C, where S is called the semi-perimeter of the triangle. So semi-perimeter is just the perimeter cut in half. So the perimeter of this triangle would be the A plus the B plus the C, and the semi-perimeter would just be 1/2 that. So you figure out what your semi-perimeter is first. That's what you're going to use for all these S's, and then you take the difference between that semi-perimeter and A, B, and C, take the square root of the whole thing, and you have your area. So let's try it out. Suppose that you own a triangular lot, like a lot of land, that has sides of 371 feet, 280 feet, and 160 feet. What is the area? So let's draw a picture here. So I have 371 feet on one side, I have 280 feet on another side, and I have 160 feet on the third side. We don't know a height, we don't know any angles, so this is going to be finding the area using this Shermans formula. Now before we can use Shermans formula, we have to find that semi-perimeter S. So S is going to be 1/2 all 3 sides added up. So this is going to be 1/2 371 plus 280 plus 160. And if you punch that into a calculator, you get 405.5 feet. So that's the S that we're going to use. Then Shermans formula says that the area of this triangle is this great big square root of the semi-perimeter S times the semi-perimeter minus the A side times the semi-perimeter minus the B side times the semi-perimeter minus the C side. So if we plug in all these S's and A, B, and C, we're going to get 405.5 for the first S. Here would be 405.5 minus A, which is that 371, and then 405.5 minus b, which is that 280, and then 405.5 minus the 160. And again, that's just a calculator computation. When you are typing this into your calculator, make sure you have parentheses around all of this underneath your square root. And when you punch it in your calculator, you're going to get quite a large number. You get 20,761.2, and since this is area, this is going to be feet squared. Okay, so to finish off, what we're going to do is prove Shermans formula. This is a college course, so I want to expose you to some proofs. And this one is certainly doable. It just has a little bit of algebra involved. So the proof of Shermans formula requires using a couple of things that we've already learned. We're going to use the law of cosines, which is this formula right here, c squared equals a squared plus b squared minus 2ab cosine c. If you solve this for cosine c by subtracting the a squared and the b squared and then dividing by a negative 2ab, you get this expression right here, and we're going to use that a little bit later on. We're also going to use the area formula that we talked about today for the area of a triangle knowing side, angle, side. So the two sides A and B and the angle C in between. So that's this 1/2 AB sine C formula. So let's start with this area formula right here, and what we're going to do is we're going to manipulate it. And remember, all we have working for us is our triangle where we know the three sides A, B, and C. So the angle C would be this one up here, in between sides A and B. So let's start with our area formula, and I'm just going to do a little bit of algebra on it first. The very first thing I'm going to do is I'm going to square both sides. So that's going to maintain equality. I'm not really doing anything that's going to create a different solution here since I'm doing it to both sides, but I'm rewriting it in a slightly different form. We're going to get a squared on the left, and if I square the right side, I'm going to get a 1/4. I'm going to get an a squared, a b squared, and a sine squared c. Now the next thing I'm going to do is I need to replace this sine squared with a cosine. I want to get cosines involved, and we'll see why in just a moment. So what I'm going to use is that Pythagorean identity, which says sine squared plus cosine squared equals to 1, but I'm going to use that solved for sine squared. So in other words, if sine squared c plus cosine squared c equals 1, then if I solve this for sine squared, then sine squared must be 1 minus cosine squared. So I'm going to substitute in 1 minus cosine squared c. And then that is now a difference of two squares, 1 squared minus cosine squared. That means it factors into a difference of squares. So we can factor this into a 1 and a 1, a cosine c and a cosine c, and I would need one of these to be plus and one of these to be minus in order to get no middle term. So far everything that I've done here is just a little bit of algebra. Now at this point, what I'm going to do is use that law of cosines formula over here, because now that I have this cosine c showing up, we're going to be substituting in these values. So I'm going to do a little scratch work off to the side over here to show you what 1 plus cosine c would become, so that we can substitute the answer in for this entire expression in parentheses over here. So let's figure out what it becomes. Well, by solving the law of cosines for cosine of c, we get this whole fraction right here. So we want 1 plus this whole fraction. Now in order to add 1 to that, you can't add a fraction plus 1 without getting a common denominator. So I'm going to rewrite 1 as 2ab over 2ab. So that's still equivalent to 1. But now that I have my common denominator, I can consolidate this into 2ab, and that means I'm left with this 2ab plus a squared plus b squared minus c squared on top. And what I want you to notice is I'm just going to rearrange the terms slightly right here. I'm going to put the a squared first, then the 2ab plus the b squared. And that means that what you have right here is a nice trinomial that factors into an a plus b quantity squared. So all of this is what 1 plus cosine c equals. Now when we get that 1 plus cosine c is equal to this fraction, there's one last thing we're going to do to this to manipulate it. If you look at the numerator, we have this quantity squared minus c squared. So that in and of itself is another difference of squares as well, which means this numerator can factor again. So what we can get are two sets of parentheses. I would need an a plus a b times an a plus a b to get an a plus b squared. I would need a c and a c to get the c squared, and one of these needs to be plus and one of these needs to be minus. So this whole quantity right here is what we are going to substitute in. All of this is going to replace this 1 plus cosine c. So all of this first parentheses becomes a plus b plus c times a plus b minus c all over 2ab. Now through a similar process, I'm not going to do it all out for you, but through a similar process it's easy to show that 1 minus cosine c is going to look very similar to this, but it's going to end up having c plus a minus b times c minus a plus b all over 2ab. So we're going to use that to substitute in for this second set of parentheses right here. So c plus a minus b all over 2ab, and a c minus a plus b as well. So here's my new expression. Let's clean it up just a little bit. Hopefully you see that the a and the a on the bottom are going to cancel the a squared that we have on the side. The b and the b on the bottom cancel out the b squared that we have on the side. So what we end up with is a plus b plus c times a plus b minus c times c plus a minus b all over c minus a plus b. And all of this is over 4 times 2 times 2, which is 16. But what I'm going to do is I'm going to break up that 16 and give each of these factors on top a factor of 2. So we still have 16 on the bottom, but I've just broken it up so that I'm creating 4 individual fractions. Now what you want to notice here is this one is exactly our semi-perimeter. That is S right there, because it's all 3 sides added up, so that's your perimeter, divided by 2. And then if we look at these other 3, they turn out to be the semi-perimeters minus the different sides. So let's see why. If we take a look at semi-perimeter minus a, for example, that would be a plus b plus c all over 2. That's what S is. And then we would want to subtract a from that. So we can't subtract these two things until we get a common denominator. So let's turn this a into a 2a over 2. So now I have my common denominator of 2. And if we simplify on top here, we're going to get a minus 2a, which is a negative a, plus a b, plus a c. And which of these up here is that equivalent to? That's this one right here. That has the positive c, it has the minus a, and the positive b. So this guy right here is S minus a. It turns out by similar computation that this one is S minus b, and this one is S minus c. So each of these is related to that semi-perimeter S. Now we're almost done. Remember what all of this was equal to? Remember up here what we did at the very beginning? We had to square both sides in order to get that sign squared in there so that we could use some trig identities. So all of this stuff, this S, S minus C, S minus B, and S minus A, that was equal to A squared. So what would just A equal? Well, I'd have to take a square to both sides. And we're talking about area, so I only want to use the positive square root. And here is where our formula for Shermans formula comes from. So the area is the square root of S times s minus c times s minus b times s minus a. So this proof involves a little bit of trigonometry because we did use a couple of identities, we used the law of cosines, but most of it is just a little bit of algebra and manipulating the formulas that we know to become things that we can use to help us reduce this in terms of that semi-perimeter. Alright, that concludes our lecture on area of a triangle. Good luck.